Now, we've been here for 2 weeks, and I've tried to get into several topics that involve the experimental point of view of phase transitions and things. And we have mainly confined ourselves to real materials which you can hold with your hand, bulk materials. They were the shape memory materials with which you can do, you can study magnetocaloric effects and things. Now, and then at the end, I told you a little bit about some more detailed experiments concerning neutron diffraction and how we can go more deeply into the thing and what kind of information we can extract. And now, more or less, much is also similar to the case when we have nanoparticles. Now, nanoparticles, the motivation behind nanoparticles, I don't have to explain this very much, perhaps, but it ranges from all sorts of applications, to sensors, to medical applications, to magnetic storage, and all sorts of things. From our point of view, what happened was that we were involved in research on these INVAR properties and things in the earlier days. And when those projects sort of came to an end, there were several options, and one was going into nanosciences. Why? Purely because of the fact that it was popular. I mean, that's how things develop, you know. In the what was it? In the I would say around the end of the 1950s, 1960s, people were studying Fermi surfaces and things. Magnetism was being more new and things. And then Fermi surface topology studies were very popular. And then 1970s, spin glasses came. And before people understood what was going on, then everybody was working with spin glasses, but spin glasses was a new phenomena. And well, it was interesting, yes, but everybody jumped on it, and it was a good way of escaping from what you couldn't do anymore. I mean, you were stuck in some places. And then what came after that? Well, after that, high TC superconductivity came, yeah? High TC superconductivity came, and before people could really solve the spin glass problem, they abandoned it, and then they got into the superconductivity. So superconductivity was very popular, and then there was a study of the magnetic properties of intermetallics and things like that. And then it got to a point where everybody got stuck there as well. And suddenly everybody started saying nano. And then people went, so, I mean, we're not very sincere with ourselves, in a sense, yeah? We're populistic in that sense. But if you, I mean, if you talk to people and things, if you talk the spin glass problems, if you talk about Fermi surfaces and things like that, it's not that the interest is lost. It's that its popularity becomes lost, and that's not the best way of looking at it. So now, anyhow, we did go into these nanoparticles. In fact, it was a project, and this project was with the engineers, and the engineers didn't know anything about magnetism, but they were leading the project. So magnetism was taboo in the beginning. We were not allowed to talk about magnetism at all. We were working with things like lead sulfide. Lead sulfide has interesting optical properties. You make nano lead sulfide. I don't know, there are some other effects, the moth eye effect, which you encounter in moths in their eyes. They have a nanostructure so that when the light comes in, it's not reflected, it's transmitted. And when it's not reflected, the predators cannot see the moth at night, and so they're not eaten up. Yeah, but somebody, Bernard, I think it was, one of these people who put the first electron microscope together, the scanning electron microscope. So if you make a scanning electron microscope, you put anything you find underneath it, and you look at it, and they looked at moths, moth eyes, and they saw this interesting structure. And this, they realized that this interesting structure gave this interesting property of being able to transmit light and not to reflect light, just because it was structured on a nanoscale, so that it could absorb, due to its characteristic, the light that was coming in and not transmit it. And this had interesting consequences. If you do this on a larger scale, then you can also absorb larger wavelengths. So you build soundproof walls. The origination of the soundproof walls that you have in studios and places like that comes from the moth eye effect. And then if you go further, if you visit Europe, you'll find that on these highways there are these soundproof walls. And that is also based on the structure that they had found in these moth eyes at that time. So anyhow, these were the things that we were studying, but we got to a point that said, look, our expertise is magnetism. How are we going to implement our expertise on the subject of nanoparticles? I mean, nobody can make this subject a taboo subject. So we got together with another colleague who was a former PhD student of ours, Bernd Rellinghaus. He's in Dresden now. And we said, look, let's do something ourselves. The name of the project was Nanoparticles Out of the Gas Phase. Okay? So that was interesting in the sense that people did make nanoparticles, but they did them with wet chemical methods. And if you do them with wet chemical methods, they can be quite messy. You can get them in larger quantities, of course. So there were several methods of available, and one was this, in that time, there was a study on cluster physics. So you have atoms of clusters which you study as the clusters grow. Now, if you have 3 atoms, you have 2 dimensions. You need 4 atoms to make 3 dimensions. Yeah, if you have 3 on a triangle, that's 2 dimensions, so you have to put 1 on top. So you have a cluster. And then you can build these, but there is no long-range structural ordering until you get very big, and then you come from this cluster state to the crystal state, and that's how crystals are built. And then they can be BCC, FCC, or whatever. So people made clusters by some fancy techniques involving sputtering and things, and we adopted this technique, and we made nanoparticles in the gas state by sputtering, generating a plasma, and rapidly quenching the plasma so that it precipitates, just like rain, clouds. And then you have a rain of nanoparticles which you collect somewhere. So as I go along, you'll see better what we are doing. The system that we took into hand was, at that time, beginning to be studied for magnetic storage. You know, for magnetic storage, you require magnetic material that has a large coercivity. So, some cobalt compounds and things like that are used for that. Now, if you could, how would you increase the density of your magnetic storage? You can make the particles, or you can make the regions where you have the magnetism smaller and smaller, so that you can write information on smaller spaces, and at the end you have a higher density of information. One material which has a very large magnetic anisotropy is iron platinum. You see a lot of this in the literature, actually, and in fact, right now, Seagate is even working on this, trying to bring out new products based on this. Now, iron platinum. We talked about this yesterday. We talked about iron nickel. And nickel and platinum are the same thing, except one comes under the other. They have, electronically, they're the same. Platinum is, what do you have? Nickel, palladium, platinum. Platinum is a 5D. Yeah, it gets larger and larger. It gets more and more expensive when you go down. And, but it's isostructural. And as you may recall yesterday, we had a path from anti-invar to invar with increasing electron concentration, with the change of the energy difference. We had on one side iron, and then we had iron 65, nickel 35, and then we went up, we had iron 50, nickel 50. Iron 50, nickel 50 has the same electron concentration as cobalt, so cobalt is iron 50, nickel 50 in a sense. And so is iron platinum, okay? So you can see here that these interesting things can be quite related to one another. How is a different story, of course, but certainly the instabilities that we encountered in iron are also carried to the nanosciences over iron platinum, and you're sitting at a composition of iron 50, nickel 50, which also shows strong magnetovolume effects and invar effects in that sense. So anyhow, but there's a slight difference in iron platinum in the sense that iron platinum in the disordered state, that is when the iron and platinum atoms are randomly distributed all over the place, it will be face-center cubic. But then if you can order iron platinum, it will be L10, okay? You can represent L10 with this figure. So actually, what do you have here? You have here two cases. You have here FCC iron, iron in a cubic environment, and you can have iron nearest neighbors and iron next nearest neighbors, but in all cases this is ferromagnetic. But when you come over here, you see that iron takes up certain places, and iron is very orderly placed in the lattice, and you have the platinum sitting on these sites. So you have a layered structure of iron platinum going on like that, yeah? And this has a very high anisotropy. What we mean by very high anisotropy is that, okay, the anisotropy, the intrinsic anisotropy of cobalt is 4 times 10 to the 5 joules per meter cube, and that's considered to be large anyhow, so that cobalt finds itself in magnetic recording media quite frequently. And iron platinum is very much larger than that. So in the event that you can stabilize this structure at smaller dimensions, then you have this tremendously strong magnetic recording material. This is the phase diagram. Now iron platinum forms three different ordered structures. You have the iron 3 platinum, you have the iron platinum, and then you have the iron platinum 3. This becomes antiferromagnetic. This is quite interesting, you know, that at small distances the iron atoms are antiferromagnetic and they get ferromagnetic, and if you increase the distance again, it becomes antiferromagnetic. So you have this oscillating exchange. And this is also true for the case of manganese. You can have manganese at small distances, you know, it's antiferromagnetic, then you increase the distance, you have it ferromagnetic. And if you put it into platinum, where you keep this distance even larger, then it becomes antiferromagnetic again. So the question is, can iron platinum particles with a diameter of less than 5 nanometers be prepared in the L10 state? It turns out that it is not that easy. So I'll take you through this and show in steps what we have basically done over here. So how to prepare L10 nanoparticles. Now, okay, we talked about the wet chemical method and the gas phase method. In a wet chemical method, in principle, you have a particles in suspension, and then you have a sedimentation, and they deposit on some kind of a substrate, and then you take that out. And after you've taken that out, you have your particles, and then what do you have to do? You have to anneal your particles, if they are in the FCC state, to be able to stabilize the L10 state. I don't think I said that. Let me go back to the phase diagram here. At high temperatures, it's all FCC. So somehow, either by the chemical process or by some rapid quenching or something like that, you come from these temperatures, very rapidly low temperatures. It turns out that you freeze in the FCC state, so the L10 state is not there. And that can happen in various wet chemical processes and in gas phase processes. So that at the end, what you have to do is you have to take your system and go up to these temperatures around here, and then you have to let it sit there so that it will acquire the other phase that you want to have. And so in the wet chemical method, if you have your particles deposited, then you have to do some kind of a post-deposition annealing on this. Now, post-deposition annealing means that, okay, your particles have come onto your substrate, it's wet chemical, you probably got other chemicals and things like that, and then you anneal it, and then what you get is, it could be a mess, okay? Because you've got the substrate to worry about, you've got the leftover chemicals and things like that to worry about over there. It's not clean, but of course, in quantity, I mean, if you could use this method properly without getting all the undesired impurities, then you have a good chance of making large quantity particles. Now, in the vapor phase or in the gas phase, what you have is you have particles somehow floating around in the gas phase, okay? And then what you can do with these is while they're floating around, you can let them fly through an oven or come into an oven, and then you can anneal that while they are flying. So if you can anneal it while they are flying, then you may be able to acquire the L10 state, and what will they do? They will deposit on a surface, and you have a clean L10 particles without any chemicals to worry about. So we put up a system that looks like this in the beginning of that project that we had. So we have a chamber here. It's our sputtering chamber. This is our gun, and this is the target. And we have here gas flowing around the target. So we have argon, and then we have helium as an exchange gas. And then if you want to, you can also put in nitrogen. Now the distinct feature about this chamber is that the outside is cooled here with liquid nitrogen. So it's sputtered in a cold environment. And the reason for that is to slow down the particles so that they can find each other and build little clusters easier. So, and then when the particles sputter, argon is the sputtering gas, argon hits the target, it rips off particles. Helium is used for to transfer the heat from the cold liquid nitrogen shield to the particles so that the particles form. And I'll come to nitrogen later, why we use that. That is a phenomena in its own. So, and then the particles fly through the sintering furnace, and they're deposited on a chamber. This is the pump that allows the whole flow here, and the flow is controlled with, of course, different control mechanisms and things. So, and this is your substrate. You have, you can vary your sintering temperatures. We call that the sintering temperatures. You set the oven. Either you don't turn on the oven, but you can turn on the oven, and you can study the effect of the of the evolution of the structure of the particles. The initial particles may have a different structure, and if you let them fly through the oven when the oven is on, then like in the phase diagram, when they come up to a certain point, they may acquire a different structure. To get particles here, unlike making films, you have to work at high pressures. If you look at low pressures, you get films. You know, you have a substrate, you have a high vacuum, an ultra high vacuum, and then you sputter, and then you get your films. But if you sputter in a pressure that is relatively high, and this is high pressure, 0.5 to 1 millibar, as opposed to 10 to the minus 5, 6 millibars, or whatever, that you would do to get films, you do this under high pressure, so that you have a saturated gas, so to speak, that coagulates. So now let's look at what we get one by one, and I'll take you through this. So you first look at these things. So when you've taken out your substrate, the easiest thing to do is to look under a scanning microscope, and you see dots. And you find that if you try to look at the sizes of these are some 5 to 6 nanometer iron platinums on silicon. And later on we found that if you want to see these nanoparticles, if you put them under an optical microscope, you can't see them, right? I mean, they're too small. But you do see them. Although they are small, I mean below the wavelength of the wave that you're using, there are reflections that come from these nanoparticles. You see indirectly the presence of nanoparticles. So if you ever go around making nanoparticles, and if you put them on a substrate that have a monolayer, just put them into an electron microscope and make a dark field lighting, and you see it. So you don't even need an electron microscope to know whether you have deposited nanoparticles or not. That's an initial check. Of course, you can't study anything, but it's an initial check to that. So then we come to higher resolution microscopy and try to understand what we have really gotten. If we look at these things under a transmission microscope, you see that they are faceted somehow. And if you try to understand what these structures are by simulating them with some models, you find that they are icosahedral structures. That is, they have 12 faces. And these faces, they're densely packed, each of them, and they are arranged so that what you have here in between are like twinnings, not twin boundaries, so they're twinned particles. They're like the twin boundaries what you have in martensite, but of course not martensite. It's just twinned, okay? So, and then here you have a plane, see? That's something like this here. I don't know whether you can see it. And depending, of course, how they are oriented according to the beam of the electron microscope, then you see the different patterns. So it's not that easy. You can't just tilt the sample holder in any direction you want. You have to find particles that are appropriately aligned with your microscope beam, so that you have a chance of understanding what the structures may be. If they are oriented or tilted in another direction, you get a pattern which is more difficult to understand. So anyhow, at a pressure of 0.5 millibars and a sintering temperature of 600 degrees Celsius, centigrade, we have not stabilized the L10 state. We also took these particles and we said, well, why don't we do post-deposition annealing on these things and see what happens. These are icosahedral particles. So we took these particles and then we took them to high temperature, at a temperature where they should transform into an L10 state, and we sit there for about 1 hour, and we see that nothing happens. And it's quite interesting. Now, this was the interesting thing that started coming out. There's no L10, meaning that the icosahedral particles are quite stable, and for some reason or another, although the L10 should be the thermodynamical ground state, also by post-deposition annealing, we don't get this. We just get things a little bit more coagulated together, but at these sizes, the L10 did not form. So then we changed the pressure of the thing. We took it up to higher pressures, and then you see what happened, and the sintering temperatures are also taken up to about 1,000 degrees. And then you find here that in certain areas you start seeing the planes, meaning that you have a certain degree of single crystallinity this time. And if you do a fast Fourier transformation, you start finding these spots which look like this, which tell you, in this case here, this is characteristic of L10. So by playing around with the temperature and pressure, you start finding regions which become face-centered cubic and L10. It appears that, okay, for example here, that would be more like a face-centered cubic, but you have anyhow a certain mixture. If you look in closer to certain regions and do some simulations, with respect to the electron beam, when you're looking like this, you see these kinds of planes, which are then characteristic to the L10 particles. Now, after doing various experiments by varying the sintering temperature and varying the pressure in the system, we come up with some kind of a morphology diagram where we see that if we are at some low pressure, independent of the sintering temperature, we get only icosahedral particles, which are about 5 nanometers or something like that in size. If we increase the pressure, then we have polycrystalline material, meaning that it's about FCC. And then if you do this at higher temperature, then you get polycrystalline and single crystalline material, and the single crystalline material is in many cases the L10 state. The single crystalline state is partially L10 state. So we're not getting anything. And this was quite surprising, but more disappointing. So we went back and thought what we could do. We went back to our experiences of what we know in magnetism and how we could use these experiences. In fact, we went back to FCC iron. We went back to the anti-invar problem, actually. Now, FCC iron is, okay, FCC is cubic, and it is possible to incorporate nitrogen into the structure. If you put nitrogen into the middle, you have FCC iron plus nitrogen, which is actually an antiperovskite. It's iron 3, iron nitrogen, in a sense. It's like manganese 3, gallium carbon, but it's iron 3, iron nitrogen, so it's an antiperovskite, and a nitrogen sits in the middle. The reason why nitrogen sits in the middle is that why nitrogen can go into the octahedral void that it sits there, it's because of the anti-invar effect. Yeah, you can expand FCC iron in all directions very easily. It has this tremendous enhanced enharmonicity, which I tried to show you yesterday. So you can make this. We said, if you can do this, iron is more or less in an FCC environment in these nanoparticles, so that if we have iron platinum, maybe we still have some leftover of the invar effect, of the anti-invar effect, which will expand the lattice and allow nitrogen to go there in the middle. So if it does that, we said, well, why don't we add a little bit of nitrogen gas and do a reactive sputtering, so that let's try to get iron platinum nitrogen like something, so that nitrogen is in there somewhere anyhow. And if we get a particle which has iron platinum nitrogen, then we'll have some kind of a structure with FCC iron and platinum surrounding it. And then if we let that fly through the furnace, then the nitrogen will leave it. Okay? So if you want to leave nitrogen, why do you put it in the first place? The reason for letting nitrogen leave is that it acts like a spoon. It stirs the thing while leaving. It enhances the diffusion properties, so that iron and platinum can diffuse and find their places with the hope of getting an L10 state. In fact, there have been some studies done on thin films on the nitrogenation of iron and platinum, and they had some interesting results over there where they stabilized the L10 structure in thin films. But there, the nitrogen was incorporated in that. So this was basically our starting point. Just to show you just once more, this is the antiperovskite iron 4 nitrogen structure. You also get hexagonal iron nitrogen, which is iron 3 nitrogen, and the hexagonal lattice it sits at these other octahedral positions. It's also possible to get that. So when we're doing this with iron platinum, we may be getting either one of these, but it doesn't matter. At the end, we want to get rid of the nitrogen anyhow. So the nitrogenation of the particles follows a path through the furnace such that you have your argon and helium sputtering gases. You need them, of course. And then in addition to that, you put in nitrogen. Then you try to react it with the zinc. So what happens, the idea is that you have your particles, and then you have your nitrogen around here, and what happens to the nitrogen sort of goes into the particle and it builds a new structure. And then here you see that nitrogen goes into the structure, and that causes an expansion of about 2 to 3% of the lattice when you put nitrogen in there. 2 to 3% is large, but it can expand. It's because of the extremely high anharmonicity of FCC iron. So that's where magnetism actually works in the sputtering process. So then your particle flies through the furnace, and as it flies through the furnace, the nitrogens leave the particle, and then they go and land on the substrate, and you take out your substrate and you try to understand what's happening. So we've got several things to prove. We have first to prove whether we get L10 particles in this manner, and the second is that does this really work like this? Does nitrogen go in there? And then does it leave it? So these are all things that have to be understood. So we take the particles, and what we see over here, that in low pressures and 1,000 degrees Celsius with about 20% nitrogen we add to the sputtering gas, we already have what we didn't have when we didn't use nitrogen. We already have the single crystalline and the icosahedral particles. So they're there. And then you can play around with the nitrogen content and so on, where you can see that you have more and more L10 parts, and then you can verify that by doing a Fourier transform on these images which you get with the transmission electron microscopy. And then if you look at it sort of all together, you find that you have particles in the range of about 5 to 6 nanometers or so. And you can really see the various facets that you get for the FCC and the L10. So this is coincidentally a good aligned nanoparticle, single crystalline nanoparticle with the beam. And if you analyze that, you see that this particular structure is that coming from an FCC structure. And then these planes, if you find something like that, then that is associated with the L10. So you can get these beautiful states. So then, if you look at a morphology diagram considering the nitrogenated particles, you get a certain systematic which tells you there are different colors here actually, okay, but they're kind of lost. So we have here, this should be black and this should be red, so this 8 and 25% correspond to black and red are twinned and icosahedral. Anyhow, the important part that we have here is this yellow part, and the yellow part is the single crystalline part. So you can see that we can optimize our conditions so that at 30% nitrogen content in the gas and at 1,200 degrees Celsius, we get quite a number of L10 particles in these systems. So now, how do we know we have these particles? There are several methods, several absorption techniques that can tell us whether there is going to be nitrogen in these things or not nitrogen. One of the techniques is the one that we use directly with the transmission electron microscope, and that is electron energy loss spectroscopy, so that your electrons, when they hit your sample, you can analyze it if you want to using this particular technique. So the energy of the incoming electrons, of course, they're selected, they come in with something, but when they're coming out, they can be absorbed by some processes so that you do not have a uniform energy that is coming out. And if you analyze the energies that are coming out, then you can see where your energy has been absorbed, what has absorbed it. And the only things that absorb them are, of course, the atoms, and each has a characteristic absorption, so that looking at these characteristic absorptions, this is taken from a lecture that you see, you get little peaks like this at characteristic positions, just like you get in an EDX analysis with X-rays or something in something similar. And then you have the so-called energy loss spectrum, and you can analyze it and see what elements and things like that have gone in there. Now, in our case, we've done this. Okay, we have our particles. Now we first look at the substrate. Of course, the substrate should contain no nitrogen. Yeah, and it doesn't show any feature of anything over there. And then we nitrogenate the particle. Actually, we think that we nitrogenate the particle, so that without turning on the furnace, if we let the particles fly onto the substrate and we take them and we look at them, we find that indeed nitrogen is there. Nitrogen has been incorporated into the particles. And the next thing is to understand whether the nitrogen has gone after that. And when we take the 1,000 degrees centigrade sintered particle, you see here that the nitrogen has indeed gone. So this idea has worked. Yeah? We nitrogenate the particles, let the nitrogen go, and let the whole thing stir the particles so nitrogen increases the diffusion. It enhances the diffusion of these things. Another method of understanding whether we have nitrogen in there is to, the primary and sintered particles. Okay, I mean this is the a further analysis of the energy loss spectra. So if you subtract the background, you find that if you have no nitrogen in here, it's just straight, and if you have the nitrogen in there, it looks like this. Of course, you can see here that the actual data is very, very noisy. I mean, it's a very tedious process. And to extract information is also not that easy. But you look for it because you have the electron microscope at home and you have the eels, so it's a good idea to look at it, that's it. But when you see something like this, you have to go into further confirmation. This is all averaged data. Yes, it looks like this, it's not too bad, but then you have to go to a synchrotron and do something better. And if you do that, you can directly see that in the room temperature particles, that is the non-sintered particles, you have practically no change, no absorption, and at the 1000 degrees centigrade sintered particles, you see clear absorptions. So that your EELS is actually doing a good job. It's noisy data, but here you see everything more clear.
1000 degrees should not have nitrogen and the room temperature.
You're right. I didn't notice that. Yeah.
Because that's the nitrogen that is.
No. It's true. No, the okay. This is red. It's this one, and this is black. It's correct. It's correct. Now this is room temperature. I explained it the other way. This is room temperature. Okay. So at room temperature, yeah, you're right. At room, the colors. At room temperature, you have nitrogen in the sample, and the room temperature sintered. And when you let it sinter at higher temperature, then the nitrogen goes away. Yeah. Okay. Good. Yes, well, you're interested in the magnetic properties of these things, yeah. And so at some point, you have to measure the magnetization to see what you've gotten, yeah. So take this and you make magnetization measurements, and what you find is at these temperatures, when you have not used nitrogen, you get at most you get some icosahedral and some FCC particles together, which give you a coercive field which is not very high. It's about 530 Oersteds compared to what it should be. It should be about it should be around up to 4 Tesla or something like that, but it's not too high. Anyhow, so the icosahedral and the FCC, they look something like this. If you put in nitrogen in the most optimum cases, then it goes up to about 850 Oersteds. It's still not the best. But over the years, as you improve your systems, change your parameters, like slowing down the particles as they fly through the furnace, because the flight time is in the order of milliseconds. If you increase these towards the seconds and do things, improve states, then you get to a point where you can actually acquire coercive fields in the size of the order of 2 Tesla. These are particles of 5.3, 10, and 15 nanometer particles, which have been annealed at about, again, 1000 degrees centigrade. And as you can see, that these coercive fields do increase. And this is a case when no nitrogen is used. This is the last of what we had done for these things. So then, this gives you, of course, very interesting information. And what you could do further is, what we have done is we've taken these particles and done some X-ray magnetic circular dichroism, XMCD. So you go to a synchrotron and you use polarized right. You get polarized light there. You get linear polarized, left circular polarized, right circular polarized, okay? So, and if you go in with the proper energy, you can, in a normal absorption experiment, you go to these L2, L3 states, and then you can shoot them up and detect them over here by some methods, and you get an absorption pattern. But if you go in there with circular light, left circular and then right circular, the absorption for left circular and right circular are different. And because they are different, they, you get different absorptions, and if you subtract one absorption pattern from the other absorption pattern, you get patterns that look like this. And from these various areas and things like that, you can extract information on the spin and the angular moment. So basically what you have is you have one absorption pattern in, let's say, in one circularly polarized direction, and then you have the other one, and then if you subtract it, you get these for the L2 and L3 states. And with some modeling and so on, you can get various information on the particles. So what we've taken with us is the good particles that we had. That was the 1,000 degrees centigrade particles in 20% nitrogen, and then when you take these particles along with you, they get oxidized. Yeah, and oxidation causes other effects, and on the XMCD data, so that one way or another you have to get rid of the oxygen before you can really understand what these are, what these things, if you want to extract information on the spin and angular magnetic moments. So you take your particles, we call it not etch, it's just the regular particles, it's the as is if you take it, and then you plasma etch them. So everything's in ultra high vacuum, and then there's a little plasma chamber, you put it into a plasma chamber, and then you clean it with hydrogen plasma. So the hydrogen takes away the oxygen, and you're left with whatever material you have. It doesn't do anything to the rest. And then if you look at the dichroism before and after, unfortunately the colors are here not reproduced. You get a better intensity or you get a better data after the plasma etching, and from there, looking at these two areas, you can estimate the ratio of the spin to the angular moment, so that, well, you get these numbers which then are related to the quality of the particles that you have generated. Now there's one thing further that is interesting, what we have done. In this project we had also some chemists working with us, and they gave us the idea of putting a surface of a layer of lipid onto the substrate where the nanoparticles are landing. So we can place them on a lipid, they will be mobile, and maybe they can self-organize one way or another. So if you embed the particles in a lipid, the lipid is a so-called, it has a funny name, I can't even pronounce it, dppc, okay? These attach to the nanoparticles, and they form these little gear-like structures. So these can go into each other, or they can remain separated. So these particles are embedded in this called DOPC. DOPC turned out to be the best lipid where these things work. The other ones didn't work that well. Now, when you take these and you let them sit by a certain temperature and with a certain degree of humidity, you find that your particles are on the lipids, they swim around, but they're separated to a certain extent. And if you look at with a certain program the separation of these particles and you Fourier transfer them, you see that in one case, at a certain Q, it's a Fourier transform, so the particles are separated by a certain preferred distance, and when they are held at this temperature at another humidity, then the particles have another distance, one at 9 and one at this. And knowing the length of these lipids, we see that in one case you have the particles well separated with the lipids, and in the other case the particles come much closer together and they kind of gear up. So in one case it's 12 nanometers, in the other case it's about 9 nanometers, depending on. So these lipids can actually control the distance between the particles. And if you age these particles in a magnetic field, what's it going to do? It's going to swim around in the lipid in a magnetic field. There are going to be forces in there, so that the particles will then have perhaps another separation. And if you age these embedded particles under a magnetic field of about 9 Tesla, so these were the other two, you see that you get these beautiful structures. What you do is they're in a magnetic field, you age them, and then I think what they do is they freeze this state by irradiating it with ultraviolet light for several minutes or something, and then you can reduce the magnetic field and they stay like this. So in that case what you have is these structures, which they're hexagonally ordered, and so at the end you can have a high coercivity system and a structure which you can start building, and if you had this all surface over that, you would have well-defined positions which you can sort of write or read or whatever you want to do. So as a conclusion for this part, we have what we have done with these nanoparticles is that if we do indeed use nitrogen-assisted annealing, then we do indeed get these L10 nanoparticles. So this is the story of the nanoparticles that we have done. I wanted to mention about this at the end of all these lectures, because you can see here that even when we were working with these things, we were basing our knowledge of our previous experience of what we had on some basic magnetization aspects. Why we have an FCC structure, why nitrogen should go in there. Nobody would have thought of nitrogen going in there unless you knew something about anti-invar. So that's where things sort of how they are related. Okay. So now we've come more or less to the end of all of this. Just before ending everything up, I'll show you more or less randomly what else we can do with gas phase particle preparation. What other techniques, what other phenomena can we investigate? And one was diffusion, as you saw in iron platinum, where we can introduce nitrogen in the system and then let it go, and then we have enhanced diffusion, and we can rearrange atomic positions and get various state types we want. Sintering in the case of iron platinum led to the stability of an ordered state. Actually, if you have two atom species and if you want to bring them together, depending on how they mix, depending on their mixing energies, they will either segregate or they will form a compound, ideally. If the energy of mixing is around 0, then you form a random solid solution, like in iron nickel. Yeah, it doesn't form an ordered state in some cases. In some cases, it does. iron 3 nickel, I think. You have iron nickel 3, you have iron nickel 3, which is an ordered state. Iron 3 nickel does not form an ordered state. Iron nickel 50-50 under laboratory conditions, that also doesn't form an ordered state, but if you look into meteorites that contain iron and nickel, in iron 50, nickel 50, you find certain planes, so that these meteorites, they cool down over millions of years. So most probably, if you allow the time, some things that we don't see as compounds turn around to be compounds. Okay, so building compounds by annealing at elevated temperatures, bringing everything to the ground state. But the ground state, instead of being a compound, it could be a segregated state. Iron, silver, iron, copper, cobalt, copper. These are typical examples of materials that are immiscible. You can't mix them. You can under very, if you rapidly quench them and things like that. So I'll just show you what kinds of things you can get with subsystems like iron silver. How do you make iron silver? We have a single target, okay? So you take an iron target, you drill holes in it, and then you attach silver, and you press silver into those holes. And you hope that in the plasma you'll get iron silver of some kind. That's how you can do it with a single target. And now iron and silver, they don't mix at all. And it's very difficult to mix them. So at the end, what you get is when you make these particles, you get various structures. They look like mushrooms. So here you have silver, and then you have iron and iron oxide, and way out here you have an oxide of iron. So you can make nanoparticles, these dumbbell-like nanoparticles as they call them, of iron and silver, or iron and copper, and you may want to functionalize them. If you do line scans of EDX on these things, you see that this is red, that's iron. And if you look at the scan position of this particle, you see that there is a lot of iron sitting on this side, and there's a lot of silver sitting on this side. If you let these particles sit for a longer period of time, and then for about 5 months or so, and take them out and look at them under the microscope again, you find these divided particles, and then you find these core shell-like particles, and in the middle of these particles you start seeing voids, empty spaces, and things like that. So this is a slow diffusion process which occurs at even at room temperature. When we just let it sit for 5 months, you get other stabilized structures. So that was one other thing. Another one was the, I'll show you this. This is an interesting video here of the aged particles when they have aged completely. I'm not sure if you're going to be able to see this on the video. This will start turning, and it's not that easy to see, but you can see the void spaces that have occurred in there over the time as you have a shell, a void space, iron and silver migrates out. So this is the structure which occurs. So silver comes out, it forms a silver oxide, and the iron, as you can see here, over a longer period, which was in here initially, has moved out practically completely. The silver has taken up this place, and iron has moved into a position where it only has oxygen. So this is an example of a fast diffusion process where things don't mix at all. And we can also look at systems which segregate slower than that, and that is iron copper. If you can make a target of iron copper, again, as you do with iron and silver, and in iron copper, if you quench it rapidly enough, you do get a random solid solution. So what you have is you have about 5 nanometer particles, and these are the primary particles where you don't turn on the furnace, and if you let them fly through the furnace at a certain temperature, they segregate. And they segregate, first you have a cubic structure, and here you have a structure that is related to both segregated iron and copper. And when you look at this closer, you can analyze regions where things have segregated and not. And in this manner, you can build certain functional. You can make it attain some certain functional properties. You can attach other materials to these. They're not exhausted. I mean, there are many, many things of these. Now, I just wanted to say here that using the very basic concept of segregation of iron copper and iron silver, you can carry this on into your nanoparticle generation systems, with which where you have used your knowledge on phase transitions, actually, and implemented them on the functionalizing of nanoparticles. So basically, there are many other examples, and many other things, of course, can be done on these things. So I want to actually now sort of recall what we've been here doing for the past 2 weeks. Yeah, I've been talking, you've been listening. Yes?
I have one question. The information or the knowledge about the alloys at the bulk, is it the same at the nanophase also when they are making a lot?
Nanoscience begins at 10 nanometers. Anything higher, larger than 10 nanometers is bulk, basically. I mean, between 10 and 20, maybe you have a transitional region. But above 20 nanometers, as everything is bulk. Any property of the bulk is carried down to about 20 nanometers. Now, as I tried to show you in the iron platinum case, when you're at very small particle sizes, you build twinned structures, the icosahedral structures. When you're below that, you start from clustering. You have cluster physics is another physics, of course. I mean, you have the building of the clusters, and by the time you start building the crystal structure, when does the crystal structure start building? It starts building after about, I suppose, 1 or 2 nanometers or something like that. I'm not sure. Anyhow, but any size effect, be it a Curie temperature, structure, or melting points, you can think of any physical parameter. These are different at sizes, or they become to be different at sizes below 10 nanometers. Above 10 nanometers, it's populistic nano. Okay, below 10 nanometers, it's real nano. We even call micrometers nano sometimes. It's 1,000 nanometers. Yeah, it's a micrometer. But so the properties are bulk above us, definitely bulk above a certain size.
So So the phase diagrams which we have explained earlier regarding etanol and all other things, when we make alloy in case of such kind of materials at nanophase, then that conditions or that kind of phase transformation will not be eligible for this kind of nanomaterials.
That's right. That's right. I mean, for example, the martensitic transition starts becoming suppressed. As you go down to smaller sizes, there's a size dependence of the martensitic transition temperature, and it goes down and down. In the case of INVAR, you have the beginning of a martensitic transition at about 68% iron. And you find that if you go down below certain sizes, the FCC phase is stabilized down to, can be stabilized down to 80% iron below certain things. So these phase diagrams are not valid below 20 nanometers. Anything can happen. But above 20 nanometers, they're all bulk. Okay? So, yeah, we started with nickel titanium, and I tried to give you an impression of what the strengths, the energies involved in these transitions are with these demonstrations and things. And then we got and did magnetic shape memory. Of course, it's very interesting that some materials are very unique materials. Many of them are perhaps waiting to be discovered that have a certain property, and then you go try to find another one, you can't find one. And then what I mainly wanted to give you was how to read experimental data, how to extract information out of experimental data, when you have what kind of data you should be taking when you're doing your measurements and things, what to look for, where to look for it. To give you any idea of the formalism of the thing, I have to sit down and study it myself again, all over. But you'll be seeing this from experts, of course, in other places, in lectures and things, where people will be also telling you that secondary order transitions are fixed and like, I mean, you'll be looking at people who are working with magnetization. I didn't tell you about Errett plots, but you know, there is a method of determining Curie temperatures. You plot the M versus H over H squared, yeah? And then you have lines coming in, and then you have lines bending, and you say, aha, this is the Curie temperature, okay? Yeah, but I mean, at the Curie temperature, what do we see? We don't see a second order transition. It's all first order. So what are these plots? So there are all these questions that are unanswered, that we take for granted, and you've got to be careful about that, yeah? It's not purely second order. I mean, what are we measuring there? Yeah. After trying to give you all of what you could actually see and extract from the experiments, you may have realized that we had lots of manganese in almost all our systems that we were talking about. So we had to go back and look at the very basic, and ask the very basic question of what is manganese, after all? What is manganese doing? And we see that from understanding this anti-Enviro effect, we see that these anomalies are carried in to the materials that we're actually studying. So it's, of course, good to study materials for applications and things, but it's also good to know what you are studying and why you're studying it. Yeah? And you may even have a chance to make better materials. This is about all I have to say. So I hope I have been able to convey to you whatever I know. I hope you have benefited from this. Time will certainly tell you. It's been a pleasure being here, coming here every morning and talking to you. I hope it has been equally beneficial for you as well. And so thank you very much for attending this course.
Yes. Mario de Rombarboa.
Thank you very much. Thank you, thank you, thank you, thank you. Oh, it's another. Oh, wow, Mario Miranda. Oh.
Mario Miranda. We knew you would take Mario Miranda.
Thank you, thank you, thank you, thank you very much. Thank you, thank you, thank you. This is very nice of you. Thank you very much. Okay, like I said, if you have any questions in the future, if you have any measurements that you have in mind which can help, write me. I can try to answer whatever I can. Okay? And I hope to come back again.
Most welcome.
Okay, thank you.